In this chapter, we're going to look at aromatic compounds. That is, we're going to take concepts from the last chapter on conjugated pi systems and see what happens when we have a conjugated pi system in a ring. So, aromatic compounds are pretty common. We've already seen examples of some, most commonly benzene and its derivatives. So you've probably already seen in lab, we've used toluene, for example, in lab, and benzoic acid, and so on. All right, so these compounds were called aromatic because they originally had very distinct smells. They were isolated from a lot of essential oils, and so, hence the name, right? However, now we have a broader meaning for the word aromatic that doesn't actually involve smell at all. All right, so it turns out, ironically, a lot of aromatic compounds right now are odorless or don't have a distinct smell. So, so we have a more sort of sciencey definition for what it means to be aromatic that doesn't have anything to do with actual aromas. All right, so as I pointed out, the aromatic functional group, or arene functional group, is pretty common in a lot of compounds. You can see here a lot of pharmaceutical compounds have them. All right, so let's talk about naming benzene derivatives. So typically when you have a substituent on benzene, you use benzene as the root word, just like you would any alkane or alkene or alkyne, any other hydrocarbon, and you name the substituent before it. Now, just like with cyclohexane, if you have only one substituent, it's automatically at the number one position. You don't need to have a locant for it. So for example, if you have a chlorine coming off your benzene, it's just chlorobenzene. Just like, if you had, a chlorine coming off your cyclohexane, it would be chlorocyclohexane. You don't have to say one chlorobenzene for the same reason you don't say one chlorocyclohexane. All right. So again, for any substitution, whether it's we've got an example here of a nitro group, we have alkyl groups like this ethyl group, the nomenclature is pretty much the same. Okay. Now, that being said, a lot of benzenes with one derivative have a common name. All right. There's a common name that can be used oftentimes as the parent name. All right, so for example, I mentioned that we'd seen toluene before in lab. Toluene is just methylbenzene. All right, so methylbenzene is a legitimate name for toluene, but we often just use the word toluene, and sometimes that makes it a little bit easier to refer to the substituents on your benzene if you have more than one substituent and different types of substituents. All right, so for example, if we had something else besides that methyl group, you could treat that other substituent as your only substituent and then just use toluene as your root word. So with that being said, it might be a good idea to memorize some of these common names. And you've seen some of these before. We've seen phenol before, way back in chapter 3 when we looked at acids and bases, right? You've seen benzoic acid before. But it is probably a good idea to get used to some of these other ones that you may not have seen before. So anisole is methoxybenzene. Aniline is an aminobenzene. Benzaldehyde just has an aldehyde group coming off your benzene. So it has that carbonyl with a hydrogen. If that carbonyl has a methyl group off it, that becomes acetophenone. All right, so that's a ketone group coming off of your benzene. And then styrene, of course, is a common monomer for making polystyrene. So you've definitely heard of that before. All it is the alkene you're using for the polymerization is just a substituent on your benzene. All right. Now, if your substituent is larger than your benzene ring, so in other words, if it has more than 6 carbons, you can no longer use your benzene as your root word. All right, it's the same concept we saw when we looked at other hydrocarbon nomenclature, right? The largest set of carbons has to become your parent chain, and so in this case, the prefix, so when you use benzene as a prefix, as a substituent itself, the word we use is phenyl. Okay, so notice the difference from versus phenol, right, which is a hydroxybenzene. Here we have phenyl with a Y, and that's the sort of aryl, so the adjective form of benzene. All right. Now, you'll often see phenyl groups as substituents in a lot of molecules. So sometimes it's you can see it drawn out, and that's fine. But sometimes to save space, we just use we use the abbreviation PH for phenyl, or we use the Greek letter phi as a symbol for a benzene ring. Okay, you've probably seen the same thing with alkyl groups. Like sometimes people write Me for a methyl group or Et for ethyl group and so on. So it's kind of similar thing here. It's just like a time and space saving measure. Right. So let's start looking at derivatives with more than one substituent. Xylene is a good example of this. So xylene is benzene with two methyl groups. All right. Now, the thing with this, though, of course, is that you've got lots of positions on your benzene. So this is a good intro into where can we put multiple substituents. Because now we've got to start worrying about locants, right? So you could have 1,2-dimethylbenzene, you could have 1,3-dimethylbenzene, you could have 1,4-dimethylbenzene. There's no such thing as 1,5 because if you've moved that to that 5 position, that's really just 1,3-dimethylbenzene flipped over, right? Same thing with 1,6. That's just 1,2-dimethylbenzene flipped over. So you're still using the lowest set of substituents. Now, in addition to those typical IUPAC, numbered locants, we have a sort of, a verbal reference to two substituents this way, and that is the designation ortho, meta, or para. Okay, so when two substituents are right next to each other, like this, that's ortho. When they're the 1 and 3 positions, that's meta, and 1 and 4 positions, that's para, where they're across from each other. So please note, by the way, that this only applies to benzene rings, okay? If you ever have two substituents on a cyclohexane, you cannot use ortho, meta, or para. That's a common mistake a lot of students make. So please note, this only applies to a benzene ring. Okay, so as I mentioned, the IUPAC nomenclature is very, very similar to what we've seen before with all of our other organic compounds up to this point. So again, identify your parent chain. In this case, it's usually your benzene ring. You identify your substituents on that benzene ring. If you have more than one substituent, you want to look at their relationship, assign locants to them, either numerically or use a sort of the verbal identifier, ortho, meta, or para. And then, if you have multiple substituents, list them in order, in alphabetical order. Though keep in mind that instead of saying benzene, you can use your common name and use that substituent that is used for that common name and put that automatically at the number 1 position. Okay, so if if you have, let's say, nitrotoluene, right, where your benzene has a methyl group and a nitro group, the methyl group's at the number 1 position. Okay, and then the nitro group is wherever it is in relationship to that. All right, so let's try an example here. Okay, so here notice that we have our benzene ring, we have an alcohol group coming off of it, and 2 bromines. Now, we're going to treat the alcohol group as our number 1 substituent, and so we're going to use the common name for a benzene with an alcohol group coming off of it. Okay, so hopefully you guys remembered that that's a phenol. Okay, and if not, you should go back to that slide and start memorizing those, or at least have that slide open, or the list of those in your textbook open when you're trying practice problems on this. But that's phenol, and so you've got to look at where those bromines are in relationship to that. So of course that alcohol group's at the number 1 position. That's 2, that's 3. So 1 bromine's at the 3 position, 4, 5. The other bromine's at the 5 position. So it's 3,5-dibromophenol. All right, so that's how we would name that. Okay, so with that in mind, let's practice this with some other examples. So feel free to pause this and try these out, and then we'll go over the names when you come back. Okay, so hopefully you're back. So let's have a look at the different examples. Now, please note that over here, the ones in red are the substituents. We're going to use the things in black as our root words. Okay, so hopefully you guys have figured that out. Just because you probably figured that out as soon as you realize there's no common name for chlorobenzene. It's chlorobenzene, right? You can't simplify that. So you probably then notice, though, this aldehyde group, of course, makes this benzaldehyde. Okay, so it's chlorobenzaldehyde, but more importantly, it's 4-chlorobenzaldehyde, or para-chlorobenzaldehyde, if you want to use the common name. And so likewise here, we have a toluene, and that bromine's at the number 3 position if that methyl group's at the number 1 position, so 3-bromotoluene, or meta-bromotoluene, if you want to use that designation. And then we have 2-nitroanisole, of course, because that nitro group's at the number 2 position from that methoxy group. Of course, the methoxy group is what makes this anisole. And yeah, so that's 2-nitroanisole. Okay, also known as ortho-nitroanisole. All right, so now that we've got nomenclature down, let's look a little bit at the structure of benzene, okay, and see where some of these concepts from the last chapter come in. The structure of benzene has been understood all the way back from 1866. This was actually quite a problem back then because just going off the empirical formula, or sorry, the molecular formula, C6H6, it was kind of confusing, right? Because no one had seen a compound that saturated, right? They're like, okay, how do we get 6 carbons and 6 hydrogens to show up in one molecule? Now, Kekule is the scientist credited with figuring out that we have this ring of alternating single and double bonds. Legend has it that he had a dream of an Ouroboros, of a snake eating its own tail, and that's what it made him think of, oh, this could be a ringed compound, another version of that legend says that it wasn't a regular dream, but it was actually an opium-induced dream. But anyway, the point is that he realized we had a ring of alternating double and single bonds. Okay. Now, the other thing that's really cool here is that these are in resonance with each other. We have 2 resonance structures where the double bonds and single bonds kind of switch places. All right. So that's the other interesting thing here about benzene. It's got resonance built into it. All right. So of course back then people didn't really fully understand resonance. So he thought that there was some equilibrium process where you had a physical exchange of single and double bonds. But of course now we know with an overlapping set of orbitals, resonance is possible. And we've seen that already in the last chapter when it came to a conjugated pi system. All we have here, as I've mentioned before, is a conjugated pi system in a ring. Okay, so there's actually, so instead of an equilibrium, as Kekule thought here, as you can see with our equilibrium arrow, what's actually going on is we have resonance, right? By the way, you'll sometimes see benzene drawn like this. Instead of being drawn with 3 double bonds, you'll see it drawn as a hexagon with a ring in it. And that's just showing that the double bonds aren't locked down in one position. They're kind of in all 6 positions at once, which makes sense with resonance. Okay, now you're going to notice that this setup, this conjugation of pi bonds that we've seen, it makes benzene kind of special compared to other alkenes that we've seen. All right, if you take cyclohexene, okay, which like benzene is a 6-membered ring, it's got an alkene functional group. It will undergo all the same reactions that other alkenes will. One common reaction here is the bromine test. So if you add bromine water to to an alkene, it'll quickly change from that reddish brown color of bromine. It'll go colorless really quickly. The reason for this is that there is an addition reaction where the bromine adds across that double bond and you get the dibromo product. Okay, so especially if you're using the drops of bromine solution as your limiting reagent, you're just adding it a few drops at a time, you'll notice that the red color disappears really quickly. Okay, this is a very quick reaction. Okay, however, if you try doing this with an aromatic ring, with a benzene, you'll notice that no reaction happens. Your solution stays that reddish brown color. Okay, even though there are 3 double bonds present for that bromine to add onto, we do not see that addition reaction. Okay, so what's going on? Why doesn't that happen? Well, it tells us that the benzene is stable. It is more stable than the addition product that we would make, and so it prefers staying in this stable benzene ring format. It does not want to form the less stable addition product. Okay, so what does that tell us? Why is benzene so stable? Where's that stability coming from? Okay. By the way, if you want to quantify that, of course, you could quantify the way we've done with other alkenes, right? You can look at the the heat of hydrogenation, right? So if you look at as we add hydrogens, we can see that we look at the energy released from the from each hydrogenation reaction, from the breaking of a pi bond, which costs little energy, and the formation of 2 sigma bonds with hydrogen, which again releases a lot of energy. You expect it to roughly double, and in the case of benzene, you'd hope it would actually triple, but instead it's actually 152 kilojoules per mole less than you would expect. All right, so it's there's that difference in energy gives you an idea of the increased stability of that aromatic system. All right, so where does this come from? To understand this, let's have a look at the molecular orbitals for this, just as we did back in the last chapter with our conjugated pi systems. Okay, now here we have 6 unhybridized p orbitals if we're looking at the pi bonding and pi antibonding orbitals. All right, we're going to ignore the sigma bonds as we did in the last chapter, only focus on the pi bonds. And so again, we have 6 carbon atoms, there are 6 unhybridized p orbitals. So here are those 6 atomic orbitals, and now here they are as molecular orbitals. All right, we have 3 bonding molecular orbitals. Right, the lowest energy one is the one where everything's in the same phase. We have a complete overlap over all 6 orbitals. The highest energy one, of course, is where there are nodes in between everything. None of the 6 are in phase with their neighbors, and so you have the maximum number of nodes there. All right. Now, in between, of course, we have smaller number of nodes. We have some overlap, some nodes. Okay. Over here, it's possible to have one node, but in 2 different directions. Okay, so here we have a node going down the middle, and here we have a node going down the middle. It's just different middles, or different directions. So both of these molecular orbitals are what we call degenerate. They're the same energy. Now, it turns out they both completely fill, because when you put in your 6 electrons, 2 of them, of course, fill this lowest energy orbital here, whereas both of these, being degenerate, fill up evenly. Okay, and so the remaining 4 electrons go there. Likewise, there are 2 antibonding orbitals that are also degenerate. You can have 2 nodes here, in 2 different directions. All right. So so basically, the fact that we have a lot of delocalization here tells you that accounts for the stability that we're seeing in our benzene. This is a very stable arrangement, that you'd have to break up to form, to do that addition reaction. All right. Now, that being said, does every fully conjugated cyclic compound have aromatic stability? And the answer is no. You'd expect it to be yes. You'd be like, oh wait, these are all conjugated pi systems. We've seen that stable. they're in a ring. Big deal, right? Like that means that they should all have that stability, right? If they're all in that ring. The answer, this depends actually on the number of orbitals you have and which ones start filling up depending on the number of electrons you have. Okay, and it turns out the size of the ring and the number of pi bonds, the number of electrons you're putting into those molecular orbitals matters. It is possible to not have an optimal arrangement of this. So we call systems that are not more stable, that actually get less stable, we call them anti-aromatic. Okay, and we're going to understand how that happens. To see this, let me give you two examples of cyclobutadiene and cyclooctatetraene. We do not see the stability of benzene in these two molecules. So if you take cyclooctatetraene over here, you can do the bromine test, and it will readily add bromine across it. That reddish brown color of your bromine will disappear, whereas this does not happen with benzene, right? Cyclobutadiene actually is so reactive, it'll react with itself, right? So if you have a sample of cyclobutadiene, it'll react with another molecule of cyclobutadiene and actually go on to form cyclooctatetraene. All right. So what does it mean to be aromatic? And how do we deviate from this rule to make anti-aromatic compounds? Okay, so this is kind of one of the key questions I kind of started this chapter with that I probably pointed out to you, earlier in this course. I think even back last semester, there have probably been times when I've said like, we'll talk about aromatic compounds. We just know aromatic compounds are more stable. You'll understand why they're more stable in chapter 18, and well, here we are. What does it mean for something to be aromatic? Okay, what causes aromaticity? And there are two criteria you've got to meet for this to happen. Okay, the first one we've already talked about, right? You need a fully conjugated ring with overlapping p orbitals. So in other words, a conjugated pi system like we saw in the last chapter, but it needs to be in a ring. Okay, the second rule, okay, and this is the thing that's new for you guys, is Huckel's rule. For Huckel's rule, you need an odd number of electron pairs, or in other words, 4n plus 2 pi electrons, where n, of course, is an integer. Okay, so benzene meets this, right? For benzene, you've got 3 electron pairs, right? There's 6 pi electrons, right? So if n is 1, that's 4n plus 2 gives us those 6 electrons. It meets that rule. That's Huckel's rule. But look at cyclobutadiene or cyclooctatetraene. Okay, cyclobutadiene has 2 electron pairs, or 4 pi electrons, right? It's got 4 carbon atoms with its 4 unhybridized p orbitals, and therefore it has 4 electrons, which is an even number, right? All these are going to be even numbers. In terms of pairs, you've got 2 pairs of electrons. 2 is an even number, not an odd number. Okay? Or if we took that number 4, notice that 4 does not fit into that 4n plus 2 definition. Likewise with cyclooctatetraene, we have 8 carbon atoms, which means we have 8 pi electrons, or 4 pairs. Okay, you can see we've got 4 pi bonds here. That's an odd, so that's an even number again, so that's why it's not meeting Huckel's rule. Also, 8 does not fit into 4n plus 2, right? There's no whole number n that would give us 8 as an answer to this. Okay, so that's why these two molecules are anti-aromatic. Okay, so why are these things anti-aromatic? Why are they less stable? Well, let's try drawing the molecular orbitals for cyclobutadiene to help illustrate this. Okay, so if you draw the 4 molecular orbitals for this, of course, the one where everything overlaps, that's going to be, down here, the lowest energy, that's your bonding molecular orbital. It looks like this, right? Everything's in the same phase. Likewise, you're going to have a clearly anti-bonding one where everything's in opposite phases, right? So you'd alternate, like, up, down, right? So this and this one would be flipped, okay? And that would be your anti-bonding molecular orbital. However, there are 2 non-bonding molecular orbitals here in the middle, Okay, they're non-bonding because they're kind of in between antibonding and bonding. They're like dead in the middle. You can't really say they're on either side of that divide. So we call them non-bonding as opposed to bonding or antibonding. Okay, this is where you have one node, and again, these two orbitals are going to be degenerate with each other. You could have these two have the same phase, and these two have the same phase, but they'd be the opposite. So in other words, if we flipped these two, you'd have a node running down the middle. Likewise, if we flipped these two over here on this side, we'd have a node running this way. All right. So those are the two non-bonding molecular orbitals. All right. So when you put 4 electrons, okay, your 4 pi electrons into this molecular orbital system, of course, 2 of them will go down to this lowest energy bonding orbital, but the remaining 2 have to split up between these 2 non-bonding molecular orbitals. All right, think Hund's rule, right? You can't, if you've got degenerate orbitals, that's orbitals of the same energy, they split up before they start pairing up. Okay, now it's these unpaired electrons that makes this molecule more reactive and therefore anti-aromatic. Okay, likewise with cyclooctatetraene, we have a similar problem, right? So here are all the orbitals for all the molecular orbitals you'd have for cyclooctatetraene. Again, you have these non-bonding molecular orbitals in the middle here, and when you look at the 8 electrons 8 pi electrons that you have for cyclooctatetraene, 2 go into this lowest energy orbital, 4 go into these 2 degenerate orbitals, and that leaves 2 left over, and they are split between these 2. Again, you have unpaired electrons here that make cyclooctatetraene very reactive and therefore anti-aromatic. Okay, so that's basically it. That's where anti-aromaticity comes from. It's just the way these orbitals and the electrons that fill them up shake out based on just numbers of these things. All right. Now, a little note here about cyclooctatetraene, because anti-aromaticity means that your molecule is particularly unstable. It's sometimes better from the molecule standpoint to just not be aromatic at all, or even like meet either of the criteria for aromaticity. So instead of being a ring of conjugated pi, of conjugated pi bonds, of having like those p orbitals all lined up, it actually puckers. It goes into kind of a boat or a tub shape to avoid having that overlap. All right, so that way it becomes actually kind of non-aromatic as opposed to anti-aromatic. It's not really aromatic or anti-aromatic. Okay, so let's practice this. Let's have a look at this molecule here. Have a look at this and ask yourself, according to Huckel's rule, will this be aromatic or anti-aromatic? Okay, so feel free to pause this if you want to take a second to do the math. All right, now if you're back, you're probably saying to yourself, well, if I take into account the total number of electrons, this is going to be anti-aromatic, right? If I count out all of my pi bonds, I've got 1, 2, 3, 4, 5, 6, 7, 8. That's an even number, right? That doesn't meet Huckel's rule. However, keep in mind that if we exclude this middle pair and we only take the 7 pairs that are around here on the outside, on the periphery, that would be an aromatic region, right? So that's actually a little quirk of this molecule I've drawn here. It actually excludes these middle 2. They don't get involved in the resonance structure, which kind of makes sense in a way. You just have this ring, this continuous ring of pi electrons that are involved, and this middle group is kind of isolated, essentially. Okay, and that allows this molecule to be aromatic. So this was actually a very tricky question. So don't be disappointed if you got this wrong. Okay. All right. Now, how do we figure out the molecular orbitals for these aromatic or anti-aromatic compounds? Right. There's a shortcut to doing this. We can draw what's called frost circles. Okay. The shortcut to this is you take a circle, and you're essentially going to draw your aromatic compound in the circle. Okay, which makes sense, right? There's one molecular orbital for every p orbital, and there's one unhybridized p orbital for every carbon in your molecule. So it makes sense that if by drawing your molecule in the circle, you're essentially drawing all the molecular orbitals. Due to the symmetry of the molecule, it actually is a great way for keeping track of the which orbitals are degenerate, because if you essentially you want to set one point of your molecule touching the bottom, because you're going to have one orbital where everything overlaps perfectly, right? Where all of your p orbitals are in the same phase. So that's going to be your lowest energy orbital. So you always put that point at the bottom of your circle. Okay, and then of course, by looking at where things are, you've got the symmetry of this molecule as it is. Wherever the points touch the circle, that's where you've got a molecular orbital, right? So you can see here, of course, we've got that first one, that lowest energy. Notice that due to the symmetry of the molecule, we have a degenerate set over here, we have a degenerate set over here, and it turns out we have a degenerate set up here as well. All right, this is a seven-sided, aromatic compound, or anti-aromatic, I guess we'll find out. But basically, it's with 7 carbons, that's how the 7 carbons shake out in terms of their orbitals. You have that one lowest energy orbital where everything overlaps, and the remaining 6 orbitals form 3 degenerate sets. Okay, now the diameter of your circle going this way is going to be the divider between bonding and anti-bonding. Okay, so anything below that line is bonding, anything above that line is anti-bonding. Anything that's on the line will be non-bonding. All right, so that's the distinction there. Okay. All right, and then at that point, you then start filling in your electrons. So if we've got 7 carbons here, we're going to fill in 7 electrons, right? So we've got 1, 2, 3, 4, 5, 6, and then there'll be a 7th one up here, which would make this anti-bonding and unpaired and therefore anti-aromatic. So if this were just C7, H7, and it were neutral, this would not be a stable molecule. However, usually this would actually be a cation, so you'd actually be missing an electron. Okay, so that unpaired electron would be missing there, and you'd have only bonding electrons here. Which, note by the way, still meets Huckel's rule. You'd have 6 electrons that you're filling in here, which meets Huckel's rule, and that would be aromatic. So, speaking of Huckel's rule, we can actually use these frost circles to understand why Huckel's rule comes about. So if you look at these frost circles for any number of carbons, right? So you can see it's drawn out for 4 through 10-membered rings. Notice that all of these examples have an odd number of bonding molecular orbitals, right? We always have an odd number, and that explains why when these things are completely filled, we meet that 4n plus 2 rule. We have an odd number of electrons. And so again, if you pair up electrons in there, you will have a 4n plus 2 number of electrons. So the frost circle just kind of graphically explains what Huckel's rule explains kind of numerically. All right. And so just to reiterate, to have an aromatic compound, you need to meet those 2 criteria. You need to have a fully conjugated ring of overlapping p orbitals. So essentially have a ring of sp2 hybridized atoms, or at least atoms that can contribute p electrons to a ring. Okay, and of course you need to meet Huckel's rule. You have an odd number of electron pairs, or in other words, 4n plus 2 electrons. Anti-aromatic compounds still meet that first requirement, that first criterion. It's just that you have an even number of electron pairs, or 4n pi electrons. when you total up those electrons, and that's why they're anti-aromatic. Now, of course, if you're not meeting that first requirement, now you have a non-aromatic ring. So again, like anti-aromatic and non-aromatic are not the same thing. Okay, anti-aromatic involves an active destabilization. Kind of the opposite of what aromaticity does. Whereas non-aromaticity just means it's not aromatic. It just, it's not really meeting that first requirement. All right, now let me introduce you to the concept of annulenes. So an annulene is any ring that includes, a fully conjugated pi system. Benzene is really just a 6-annulene. So the number in front tells you the number of carbons that are involved in the ring. Okay. Now, out of these, annulenes can be, you have some aromatic ones, some anti-aromatic ones. You really just have to look at your number of pi electrons. If you've got an odd number of pairs, then it's going to be aromatic, and if it's an even number of pairs, then it's anti-aromatic. Okay, so all these examples here you'd expect to be aromatic because they've got odd numbers of pairs. So like we've got 3 pairs here in benzene, which obviously we know is aromatic. Here for 14-annulene we have 7 pairs, and that's again an odd number. Now if we look at 10-annulene, you'd probably expect that to be aromatic as well. You've got 5 pairs here, in your 5 pi bonds. Why isn't that aromatic? It actually winds up being non-aromatic. It's not anti-aromatic or anything like that. It's non-aromatic. See if you can figure it out just by looking at it. I'll give you a hint. There is a sterics reason for this. Okay, so if you're thinking about this carbon over here, and remember it's sp2 hybridized, so it's trigonal planar, there's a hydrogen that's not shown that's sticking out over here. Likewise, there's a hydrogen over here that's also sticking out. Those 2 hydrogens can't overlap, right? So it's actually due to steric hindrance. That steric repulsion causes the ring to pucker a little bit, and you don't have a perfect overlap of all those p orbitals. It's not completely flat. All right, now I alluded to this earlier when we talked about that 7-membered ring, but basically sometimes to get an aromatic number of electrons, you actually have to have a formal charge involved. Consider this 5-membered ring here. All right, so you want these 3 bonding orbitals to be completely filled, so you need 6 electrons in here, but this would have only 5 electrons contributed from its 5 sp2 hybridized carbon atoms. So it needs to pick up an extra electron to have 6 to meet Huckel's rule. And in doing so, it's going to have a negative formal charge. So if you want to see what that looks like, so here's cyclopentadiene, and of course with that negative formal charge, it has that, it's a carb anion. And remember, these aromatic systems are resonance stabilized, right? So that negative, that carb anion is spread throughout the molecule through resonance, right? It's moved from carbon to carbon accordingly. This actually has some interesting effects when it comes to acidity. Okay, and you'll see in the case of some other aromatic compounds, even basicity is also affected. I'll come to that in a second when we talk a little bit about heterocyclic aromatic compounds. But look at cyclopentadiene as a neutral molecule. All right, now when you look at that sp3 hybridized carbon, you say, okay, that's an sp3 hybridized carbon. To pluck off one of those hydrogens, I'd expect an acidity that's closer to that of, let's say, ethane, right, or any other alkane, which is somewhere in that ballpark of 50. Instead, it's a much lower pKa. It's closer to that of an alcohol. And the reason for that is that when you pluck off that proton, okay, that resulting conjugate base is going to be aromatic. It's this molecule we've drawn over here, right? We pluck off that proton, and that resulting carb anion is now aromatic. Okay, so we have a very stable conjugate base, and that's why the pKa is so low. All right. I've kind of already talked about the seven-membered ring, but again, I pointed out that if you have seven electrons in here, you wind up having an unpaired electron up here in this antibonding orbital. So if you get rid of that and you have only these 6 pi electrons, again meeting Huckel's rule, you would have an aromatic system. And in order to do that, this winds up being a cation. You wind up having an electron missing, so you have a positive formal charge. Again, these are all resonance stabilized, and so you can see that formal charge jumping from carbon to carbon, throughout the ring. So I mentioned earlier that you can have aromatic compounds that are heterocycles, where you just simply swap out a carbon in your ring for something that's, well, not a carbon, usually a nitrogen or sometimes an oxygen, but nitrogen containing heterocycles are pretty common for aromatic compounds. For example, pyridine is a pretty common base you'll come across, where we swap out one of the carbons for nitrogen. All right. Likewise, pyrrole is an example of a heterocycle where we take cyclopentadiene and we swap out that sp3 carbon for a nitrogen accordingly. Okay. In the case of these heteroatoms, you've got to take into account the different number of electrons and how that plays a part in the aromaticity. We have an interesting effect here, which you also have to take into account when looking at the basicity of these molecules. All right, so let's see how these are involved. Basically, you probably ask yourself, is that lone pair on that nitrogen involved in this aromatic system? Do we need this or not? And the answer is maybe. It depends on whether it's necessary for meeting Huckel's rule. If it is, then it's going to be used, and we're going to see that in the case of pyrrole. If it's not necessary, then it's not used, and that's the case that we see in pyridine. All right. Now, this is actually what leads to their basic properties. So pyridine, I mentioned, is a very common base, and the reason for this is that its lone pair is not used for the aromaticity. So if I go back to this picture here, you can see that the unhybridized p orbital on that nitrogen is available to use for our conjugated pi system. This is an sp2 hybridized nitrogen. That p orbital can be used for conjugation. The lone pair is actually housed in an sp2 hybridized orbital on that nitrogen. Okay, and so that's what's kind of sticking out here. And so this is available to pluck a proton from something. So we see that here. The nitrogen readily accepts a proton from an acid, and because that lone pair that's now being used to form that bond with a hydrogen was never needed for aromaticity, the resulting conjugate acid is still aromatic. This is still a very stable molecule due to that aromaticity. Okay, so that's why this is a pretty strong base, or it's relatively basic. Okay, now look at pyrrole. For pyrrole, that that nitrogen is sp3 hybridized, but we can use that p orbital. We can unhybridize a p orbital and involve it in that conjugation. Now, in order for this to work, though, that lone pair on that nitrogen has to be housed in that p orbital. So, in other words, that pair of electrons is used to contribute to Huckel's rule, right? So we have 2 electrons over here, 2 electrons here, and we have 2 electrons from that lone pair on nitrogen, and that's where we get our 6 electrons for Huckel's rule. Okay, that's what makes pyrrole aromatic. However, if we were to use pyrrole as a base, that lone pair would then get used up to form this bond with hydrogen to make the corresponding conjugate acid, which now means that we have to break aromaticity here. So this actually winds up being non-aromatic. You'd think, okay, is that going to be anti-aromatic because we've got 4 pi electrons here, but remember now this nitrogen is now sp3 hybridized, so that actually breaks. You don't have a p orbital that's available to get part of the ring, so it's actually non-aromatic Okay. Anyway, so my point here is that you lose that aromatic stability, and therefore this is way less stable than the pyrrole, which is aromatic. So you can see that that reverse reaction. This equilibrium is very reactant favored. All right, and that's why this protonated this conjugate acid is actually very acidic. All right, you can even see this in electron density maps. In pyridine, if you try to look for that electron density from that lone pair, you'll see that it's over here solely on that nitrogen. Whereas in the case of pyrrole, you can see it's delocalized throughout the ring, as you would expect for an aromatic system with that conjugated pi system. All right, so let's practice this concept. Have a look at these examples and ask yourself for each of these, are they going to be aromatic, anti-aromatic, or non-aromatic? Okay, so if you've paused this and come back now, here are the answers. Okay, the first one's pretty straightforward, right? You've just got a nitrogen here, but if you swap that out for a carbon, you basically have cyclooctatetraene, which we've seen is anti-aromatic. We have 4 electron pairs here of pi electrons. That's an even number. It's going to be anti-aromatic. Now, let's look at this example here. This is interesting. You might say to yourself, okay, is this going to be aromatic or anti-aromatic? Well, in order for this to be a fully conjugated ring, one of the p orbitals on this oxygen has to get involved in that ring, in that conjugation. Now, in doing so, one of these lone pairs would be in one of those p orbitals. So now you have 1, 2, 3, 4 electron pairs, which is an odd number, which is anti-aromatic. So rather than be anti-aromatic, this oxygen stays sp3 hybridized. It refuses to get involved, and it will prefer energetically to be non-aromatic than to be anti-aromatic. Okay, so it winds out that this stays sp3 hybridized and actually kind of puckers the ring a little bit and prevents that overlap, that conjugation. Over here we have 1, 2, 3, 4, and a 5th pair of electrons. So you can see here that this has to get involved to give us an aromatic number of electrons to meet Huckel's rule, but it does, and so we have an aromatic system. Now over here we have an MTP orbital, which we've seen can overlap with things to make that conjugated pi system. Now we've got 1, 2, 3, 4 pairs of electrons, so that's an anti-aromatic number. So this is going to be, well, it would be anti-aromatic. That's of course assuming that it stays flat. This might, like this molecule over here, might prefer to be non-aromatic than anti-aromatic. So it's possible for this ring to pucker and avoid being flat, and therefore avoid that anti-aromaticity. Okay, now it's possible to have fused ring systems that are also aromatic. You've seen examples of this probably. You're probably familiar with naphthalene. It's the common ingredient, the active ingredient in mothballs. Okay, so you've probably smelled naphthalene at some point. Just if you've ever been in an antique store, or just gone through in an old closet. But basically, it's a benzene ring with another benzene ring fused onto it. If you fuse on a third benzene ring, you get anthracene, and of course that's all fused in a row. If you kind of connect them in this sort of V shape, you have phenanthrene. So these are all examples of polycyclic, multiple fused benzene rings, making polycyclic aromatic compounds. Now, if you're trying to see how these meet Huckel's rule, you can quickly see that adding each additional ring adds 2 more pairs. But since you started off with an odd number of pairs, you're still going to have an odd number of electron pairs and therefore meet Huckel's rule. All right, so with naphthalene, you've got 5 electron pairs. With anthracene and phenanthrene, you have 7 electron pairs. They're still going to be aromatic. Okay, and of course you can prove this aromaticity using heat of hydrogenation, the same way you do with benzene. Okay, so you'll notice that you would expect the however many double bonds to give you a certain amount of heat of hydrogenation, similar to cyclohexene or cyclohexadiene. but instead it's lower than what you'd expect because this molecule is more stable. And you're looking at that difference in energy, you can see that it increases as you add more and more rings. So if you look at the amount of energy per ring, you can see it's a roughly consistent number. Okay, so as I said, these you still have these rings of conjugated pi, overlapping p orbitals, and of course, I mentioned you still meet Huckel's rule. You have an odd number of electron pairs. That's why these are still going to be aromatic. Now, while benzene itself is pretty unreactive because it's so stable, there are positions off the benzene that are reactive, where we can do a reaction. Basically, if we have an alkyl group attached to our benzene ring, that carbon by which it's attached, that where it connects to the benzene ring, is called a benzylic position. And this is the very reactive position because it is very similar to an allylic group. Please note that the benzylic position is just one bond away from a double bond. And if you think back to what an allylic group looks like, you should see some similarities there. If I highlight that, that should kind of point that out, that we have an allylic system there. Likewise, here we have another allylic system with that benzylic carbon. Okay. The only difference here is that unlike an allylic group where it's just that one double bond where those electrons could be delocalized, here you can delocalize the electrons on that carbon with the entire aryl ring. All right, so basically you can kind of stabilize any negative charge, a positive charge, a radical, anything on that at that benzylic position. All right, and it's specifically that benzylic carbon. It doesn't matter whether or not you have any carbons extending from that. One reaction we can really, generally quickly observe here is oxidation. So, you've probably noticed that, like an alkane, you can't really oxidize benzene, right? If you use even a strong oxidizing agent like chromic acid, potassium permanganate, you generally won't see any reaction. Okay. That being said, at that benzylic position, you do see a reaction. You can, if you reacted with, in this case, chromic acid, you will convert that benzylic carbon into a carboxylic acid and make benzoic acid. Now, it doesn't matter how many carbons you have in your alkyl group, the benzoic acid always forms at that benzylic carbon, okay, and the rest of the alkyl group is kind of lost. All right. We've actually done this reaction with toluene. Toluene has just that methyl group sticking out, and we've oxidized that in lab using potassium permanganate, which is another strong oxidizing agent. All right. One caveat here is that you do need at least one proton at that benzylic carbon to have this oxidation move forward. So, for example, tert-butyl benzene will not undergo oxidation. Okay, so as I mentioned, potassium permanganate is a good oxidizing agent as well. We've done this this reaction in lab, and you probably noticed even with that reaction in lab that you actually go through the salt intermediate. You make potassium benzoate. And you probably noticed that in order to get your product, you had to add hydrochloric acid, and that's when you start precipitating out white crystals of your product out of the aqueous solution. Of course, please note that even though this carboxylic acid is capable of hydrogen bonding, that large benzene ring kind of overpowers that, and that's why it's only sparingly soluble in water. Okay, so that's why it tends to precipitate out. When we add hydrochloric acid and we protonate that site. Whereas here, in its ionic form, it's a little bit more, much more water soluble. Okay, so I've already pointed out again the similarity of allelic position. So again, the key thing is that due to that proximity of the double bond, electrons at that location, whether in the form of of an anion or a radical, or or lack of electrons, like that formal charge from a carbocation, all of that can be delocalized through resonance stabilization. Okay, so radical reactions are also very possible. You can see that benzylic site is very reactive for a free radical reaction, such as bromination. So here we can use NBS as our brominating agent. You could also use just bromine in the presence of light, and it would also brominate at that position. All right, now, just like with alkanes, which are unreactive, once you've added a bromine, once you've added that halogen to your benzene ring, now you have or not directly to the benzene ring, but you've added a bromine to this compound. Now you have a site for a reaction. You've now increased your synthetic options for this molecule. You can do all sorts of reactions. You can do substitutions, you can do eliminations, and so on, right? And then, of course, you can go on from there. Once you've done an elimination, you can add stuff across that double bond and make all sorts of molecules. Again, this benzylic position, it really stabilizes a positive charge pretty well. So that leaving group, it's a great leaving group, and it's great for an SN1 mechanism where you go through a carbocation intermediate. Of course, it's not limited to that. In this example here, we have a primary alkyl halide, and of course, that's great for SN2. My point here is that if you think back to last semester when we started looking at synthetic pathways, and we started off with an alkane, we saw that alkanes are kind of hard to do anything with. You can't really do much with an alkane. So pretty much the only option you had was to do some sort of radical reaction to get a halogen on there, a bromine or a chlorine, and then once you've got that leaving group, now you've got a whole bunch of synthetic options. So if you have an alkyl benzene, you're kind of in the same boat. You can do a bromination, and now you've got a whole bunch of options opened up to you. Okay, whether in this case you've got substitution reactions, but you can see, of course, we have elimination reactions as well, and then, of course, those products can then go on to further reactions. We can do addition reactions across these alkenes that we formed. Okay, so here's kind of a summary of that synthetic utility that we have. Starting off with an alkyl benzene, you can see that, of course, you can oxidize at that benzylic position using some oxidizing agent. So whether you're using a chromic acid or potassium permanganate, you'll wind up with that benzoic acid. Okay, and that can, of course, go on to you can do a bunch of reactions with that. Over here, of course, you can do bromination using either NBS or bromine in the presence of light. And of course, now you've got that good leaving group. You can do substitution reactions, you can do elimination reactions. You've got a whole bunch of options. All right, so with that in mind, have a look at the molecules we have here. Starting off with this example here on the left, and for each of these reactions, ask yourself, what reagents do we need? So look at, for every given reaction, look at the reactant and the product, look at your functional group changes, and ask yourself what reagents help there. Okay, so pause this video and take a second to look for it. Okay, so if you're back now, here are the answers. All right, so if you look at this first reaction here, you can see the key difference is we've added bromines at these benzylic positions, which, again, that benzylic position is the most reactive site on this entire molecule over here, right? That's going to be, pretty reactive, more so than any of those other, secondary or primary sites. So those will selectively get brominated, and that's what makes this product here. Okay, you can see for making this product, what we've essentially done is a dehydrohalogenation. We've removed the halogen, of course, and we've removed a hydrogen from the neighboring carbon. Okay, so that's an elimination reaction. You need a base to do that. please note we've made the Zaitsev product, right? We formed the double bond over here. If we form the less substituted double bond over here, that would be the Hoffman product. And so since we want the Zaitsev product, a smaller base like sodium methoxide is fine. If you used a bulky base like sodium tert butoxide, you would probably get the Hoffman product instead. Okay, with the double bond over here instead of over here. All right, and so it does that at both sites. You have a double bond over here as well by eliminating an HBr across this carbon-carbon bond, and that's how we get this product. Okay, now for the other two products, so over here, notice that that benzylic position has been converted into carboxylic acids. All right, so of course you just need a strong oxidizing agent to do that. Either use potassium permanganate and water, or you can use chromic acid in the form of sodium dichromate and sulfuric acid. And the same thing happens here. Now, this one's kind of interesting. When you do your elimination reaction, you've converted your benzene with additional alkyl groups here into essentially a naphthalene system. You've got a fused aromatic system here, but this whole region, this whole moiety is aromatic. So now we've got new benzylic positions. Over here and over here are our new benzylic positions to this benzene ring over here. Of course, if you use, you can see that we're converting those to carboxylic acids. And so, again, an oxidizing agent like potassium permanganate or chromic acid will work here. Now, I've pointed out that these were, we looked at reactions that were off of our benzene ring, right, at alkyl groups that were attached to our benzene ring. In the next chapter, in chapter 19, we're going to look at lots of reactions on the benzene ring itself. There's whole classes of reactions that are kind of interesting, including how to add that alkyl group onto the benzene ring in the first place. That's a Friedel-Crafts alkylation. We'll get into that in the next chapter, as well as a whole bunch of other electrophilic aromatic substitution reactions where we can basically add things on to the benzene ring, where we can swap out hydrogens for these other groups. But for now, we've pointed out that it's really hard to do reactions on the benzene ring. It's clearly benzene likes staying aromatic. Anything that takes it out of that aromaticity is generally kind of difficult to do. All right, so we've looked at oxidation, of course, at that benzylic position, but it's possible to do a reduction or a hydrogenation at the on the benzene itself, but as I pointed out, it's really, really difficult. Okay, so even though this is an exothermic process, like the reaction, if you look at the enthalpy of the reaction, it's a negative number, right? It's an exothermic reaction. So you'd think like, okay, this seems like it should be, energetically favorable. Look at the conditions for this, right? Notice that you need 100 atmospheres of hydrogen gas over your nickel catalyst for this reaction to go forward at 150 degrees Celsius. Okay, so 150 degrees Celsius, that's pretty hot, obviously, but the 100 atmospheres of hydrogen gas, I think, is kind of a emblematic of just how difficult this is, how stable aromaticity is, and how difficult it is to get out of that. Okay, so we need some pretty forceful conditions to get this reaction to go forward. Okay, so that being said, we can take that to our advantage. So if you have a styrene where you have an alkene off of your benzene ring, well, that alkene is a little bit easier to hydrogenate. So you can actually, using mild conditions, can hydrogenate selectively at that site. Okay, as opposed to the you can leave the benzene ring untouched, because that 2 atmospheres and room temperature is not going to be enough to change that benzene ring into cyclohexane. Okay, so that's something to keep in mind. So that being said, there are other ways that you can do your benzene reduction that don't involve as forceful conditions, specifically the Birch reduction. We're not going to take our benzene all the way to cyclohexane here, but we are going to effectively make it a cyclohexadiene. Okay, so to do the Birch reduction, you use sodium metal. All right, so sodium contributes one electron, does a single electron transfer, and it converts your benzene into a radical anion. So you can see here when we add our sodium, our electron from sodium, notice that we're using fishhook arrows here, and so our pi bonds, split up and move accordingly. So we move our double, move a double bond here. Our unpaired electron from our sodium, and one of these pi electrons converts this into an anion, and likewise the leftover electron from this pi bond winds up sitting on this carbon across from it, forming a radical. So we call this a radical anion. Again, notice we have the anion and the radical parts to this molecule. Now, to get rid of the anion part, we have methanol present as well, and methanol is protic. So this anion can pick up a proton from your methanol, and it will just get rid of the anion part. Now you just have a radical left over. Okay. So what does this radical do? Well, you still have sodium left over, so we do this again. Another sodium atom transfers an electron over. Your radical becomes just an anion now, with that negative charge, with that pair of electrons. And of course, that anion can again do a proton transfer and pick up a proton from another methanol molecule, and that's where we get our product. So notice that we have a product that has two double bonds across from each other, and the carbons that have been protonated, they're now sp3 carbons, those are also across from each other. Okay. As for the sodium and the methanol, well, your sodium atoms have now been made sodium ions, and your methanol has become methoxide. So you have sodium methoxide as a byproduct. Okay, so for every molecule of this product that you make, there's two equivalents of sodium methoxide that's made as a byproduct. All right. Okay. So so that's basically how you do this reaction. Quick note: if for the setup for this, your metal is dissolved in liquid ammonia, which kind of makes sense. You kind of don't want to take your sodium and drop it in methanol as a solvent, because the methanol is a protic solvent. You could have an explosive reaction with the sodium there. Anyway, so the key thing again is that we've got sp3 carbons across from each other in our benzene ring. Okay, or no longer a benzene ring, it's a 1,4-cyclohexadiene. Okay, so 1, 2, 3, 4. Yep, 1,4-cyclohexadiene. Now, what do we do? Where do these double bonds and sp3 atoms show up when we have a substituent on our benzene ring? And that's an interesting question. And to understand why it happens, we'll have to look at the mechanism again. So here, if we have an electron donating group, such as an alkyl group, we find that the product we make looks like this. Okay, the carbon that that our electron donating group is attached to stays an sp2 carbon. It does not get reduced. We still have our two sp3 carbons that are across from each other, but they can never be that carbon that has the alkyl group attached to it. So in other words, we do not observe this product. Okay, we have to have this product here. Okay, you could have drawn the double bond on this side and the double bond on this side, but the fact remains that carbon has to be sp2 hybridized. And to understand this, let's we'll look at the mechanism. But we see the opposite effect with an electron withdrawing group. So let's say we have an electron withdrawing group like a carbonyl group here, which remember, you have a resonance structure where these electrons get pulled towards that oxygen and give it a negative charge. This pulls electron density away from the ring because this bond has some partial double bond character. So what we do observe, though, is that that carbon specifically gets reduced. We see that as one of our sp3 carbons, and the two our double bonds wind up being on either side of it. We do not see the product where that carbon remains an sp2 carbon. Okay, so why is that? Okay, if we go back to our mechanism, you'll see that it has to do with the stability of that anion being formed, right? So if we had our electron donating group over here, okay, uh, this pushes electron density to this already negatively charged anion, and that doesn't really that isn't very stable at transition state, right? You're pushing way too much electron density on that carbon, which is not particularly electronegative. So for an electron donating group, this would not be a stable anion, okay, and that's why that carbon that the electron donating group is attached to cannot go on to become that sp3 carbon. Okay, but for electron withdrawing group, it does make sense. That kind of sucks away some of that electron density, and therefore stabilizes that negative charge. It kind of like delocalizes it a little bit, and therefore it lowers the energy of that transition state, and that's why converting that carbon into your sp3 carbon makes a lot more sense. Okay, so that's why we observe that. Okay, so with an electron donating group like an alkyl group, remember that that carbon does not get reduced; it stays sp2, and and so it's always one of the carbons next to it that will wind up being an sp3 carbon. Okay, and of course for an electron donating group like a carbonyl, electron withdrawing group like a carbonyl, we notice that that carbon is specifically reduced; it's selectively reduced. So that's definitely going to be one of our sp3 carbons. Okay, so finally, let's talk a little bit about the spectroscopy of aromatic compounds. So we've kind of already seen aromatic compounds. We've talked a little bit about them in the last couple of chapters where we've seen, like spectroscopy methods, and we've had to deal with certain aromatic compounds as examples. So you've kind of already observed this already. So let's start off by looking at IR spectra, right? Where do we observe features of aromatic compounds in our IR spectrum? Okay, so if we're looking for those carbon-hydrogen stretches, remember, carbon-hydrogen bonds generally show up in around 3,000 wave numbers. Typically, if you have an sp3 carbon, they'll show up below 3,000, but since we have sp2 carbons here in our aromatic compound, they're going to show up in that 3,000 to 3,100 wave number range. At the lower end of the diagnostic region, down where we see our double bonds, you should hopefully see the carbon-carbon double bonds in that 1,700 to 2,000 range. Though of course, we're dealing with relatively non-polar signals, and so they're generally rather weak signals here for those carbon-carbon double bonds. Once we start getting into the fingerprint region, of course, now you tend to have like a mess of peaks here, and sometimes it's a little harder to read this. But that being said, of course, as a fingerprint region, there are distinct peaks that aromatic compounds tend to have. So in that 1450 to 1650 range, you should see three medium intensity signals that represents the stretching of those carbon-carbon bonds, as well as ring vibrations. You start seeing so a couple of strong intensity signals around that 1,000 to 1275 range for the bending of carbon-hydrogen bonds in the plane, and around 1690 to 900 you'll see some signals for them bending out of the plane. All right, so if you want to see an example of this, here's ethylbenzene. So of course we've got an ethyl group that's contributing to some of this stuff. The ethyl group has sp3 hybridized carbons, so you can see all those stretches over here from that ethyl group. But you can see the stretches above 3,000, that 3,000 to 3,100 range. Those are the stretches that are on your benzene. Okay, so here your carbon-carbon double bond stretches over here in that range, and of course now here in the diagnostic region, you can see some of those distinct stretches I referred to earlier. Okay, now that being said, with NMR, of course, NMR has really distinct aromatic peaks. But the peaks themselves aren't very distinct because they're all muddled together, but they're distinct from non-aromatic carbons in that they're all the way downfield in that 7 to 8 ppm range, right? You've got a chemical shift all the way down here. It's pretty clear that these signals over here come from the benzene ring, and these over here come from not the benzene ring. They come from that ethyl group that's attached to it. So you can see that also, like, with the integrals here, the fact that you've got these 5 hydrogens here, that corresponds to the 5 hydrogens on your benzene ring, that aren't substituted. Okay. By the way, the shifting of these, the CH2 on our ethyl group, the shifting of it further downfield also makes sense because it's right next to that benzene ring. So some of that diamagnetic anisotropy also shifts that signal further down from the methyl group that we see over here. Okay. Of course, with benzene, keep in mind that it's a very symmetrical molecule. So depending on what you have, what substituents you have on your benzene ring, that might affect your number of signals, and it might affect your splitting. So definitely, keep that in mind for the number and types of signals you see in that aromatic range. For example, here, this molecule is very, very symmetrical, such that all 4 of these protons are identical, they're equivalent, and that's why you only see a singlet here. Whereas here we see 2 different types of protons, right? Because we have 2 different groups. So the ones that are closer to X are different from the ones that are closer to Y. And as a result, we see 2 different signals, and they split each other into doublets. Okay, and so again, that splitting pattern and the fact that we have 2 signals tells us something about what's on our benzene and the symmetry of this molecule. Okay, so you can see again here, changing the location of 2 groups changes your number of signals accordingly. Okay, so looking at that symmetry, we have a change in the number of signals. In this case, we're looking at carbon-13, so we're looking at those carbon signals. But again, that symmetry is going to cut down your number of signals. Okay. Oh, and of course, with carbon-13, those benzene carbons are sp2 hybridized, so they show up in that 100 to 150 range. Okay, so let's practice this. For this molecule here, go ahead and predict the for both the carbon-13 and the NMR, the proton NMR, predict the chemical shifts for your signals. Predict, in the case of proton NMRs, you can also predict the integration and multiplicity, the splitting patterns for those signals as well. Okay, so pause this video, and when you come back, we'll have a look at that. Okay, so hopefully you're back, and you've probably noticed that this molecule is pretty symmetrical. So hopefully there aren't as many signals as you thought there were. Okay, there's a lot of equivalence here. You've got to see some of this. You may have to rotate around these bonds to see where there's like kind of a you can make this molecule very symmetrical just by rotating along one of these bonds, so that both these arms coming off of this central benzene are pointed the same way, for example. Or you could simply just see that if you have this central point here, there's a rotational axis where this benzene gets rotated over here. That's another way to look at it. All right, so that being said, in the carbon NMR, there's going to be 6 signals that you see. Okay, so if you're having trouble seeing them, keep in mind that, well, I guess I can mark them on here. Basically, you have, you're going to have 7 signals. This carbon over here is non-aromatic. That's going to show up in the sp3 carbon range, okay, for that benzylic position. But the remaining 6 carbons, so these are symmetrical. I'll just call them carbons A. Okay, and of course they're the same here. Okay, these 2 here. These 2 are going to be symmetrical, or are going to be equivalent. So carbon B and this is carbon C. Okay, so those are 3 signals that we're going to see. Okay, this of course is another signal, so that's D. Okay, and on this central carbon, this is another signal, E, and then these 2 are going to be equivalent, so that's F and F. Okay, and then of course this symmetry continues on here, so these are also carbon F. Okay, they're going to be symmetrical to these. and this is also going to be carbon E, and you can see how this continues on. Okay, so there's that rotational axis for all of these. Okay, and of course this is the non-aromatic carbon that they talk about. Okay, with proton signals, of course, here are all the different protons that are shown. Okay, they only show one of each, but of course there are the equivalents to them. So this is proton D over here that's not labeled. Okay, that's going to be equivalent to that one. This is also a proton C, same to like this one. Hydrogens B over here are going to be the same as the two hydrogens B here. And of course, all these unlabeled carbons, all these unlabeled hydrogens have their equivalents as well. Okay. So, what are the, where are all these different protons going to show up? With the exception of hydrogen B, everything else is an aromatic proton. So you can see that hydrogens A, C, D, and E are all in that 7 to 8 ppm range. Okay. Hydrogen B, of course, will show up at around 2 to 3 ppm. Okay, it's going to be a little shifted down a little bit because it's in that benzylic position, close to that benzene ring. So it's going to be down to 2 to 3 ppm instead of 1 to 2 ppm. Okay, and of course you can figure out the integrals accordingly, right? So for hydrogen A, we've got these 4 over here. For hydrogen B, there's these 2 and these 2, so that's 4 again. For hydrogen C, you've got 2 on this benzene ring, but remember they're the equivalent to these 2 over here, so again you'll see 4 of them. Same with hydrogen D. And of course hydrogen E has only 1 sticking out here and 1 sticking out here, so there's only 2 of them there. Okay, so that's the integrals. What about the splitting patterns, right? How are they going to split each other? Hydrogen B is, not close enough to either hydrogen A or hydrogen C to get split by them. If you count the number of bonds, we've got 1, 2, 3, 4 bonds there. Likewise, if we look at hydrogen C, okay, so let's say we've got hydrogen B here, that's 1, 2, 3, 4 bonds again. That's not enough to split hydrogen B into anything. So hydrogen B winds up being a singlet. Okay. Same thing for hydrogen A. Hydrogen A is not close enough to anything other than another hydrogen A. So it will also just remain a singlet. You only see singlets for those. Hydrogen C and D get a little bit, well, hydrogen C, I guess, could be split into a doublet by hydrogen D. I think it's too far away from hydrogen E to be split. Hydrogen D, hydrogen D gets a little bit complicated because it gets split by hydrogen C and hydrogen E. So I guess hydrogen D would be split into a doublet by hydrogen E, split into a doublet by hydrogen C. So I guess you'd see a doublet of doublets, unless you know the J values. You might, because this is all in that aromatic region, it's there's a possibility it might be hard to read. So it looks like they've just listed them here as multiplets because there might be a lot of overlap here. Okay. Likewise, hydrogen C. Hydrogen C is interesting. It gets split into a triplet by hydrogen D because it's got it's within range of both hydrogen Ds, so it actually winds up getting split into a triplet. But again, there might be some overlap here, so they've only listed it as a multiplet because it might be hard to see. All right, and that's how those are the signals you should hopefully have gotten. Okay, so finally we will talk about materials that take advantage of these aromatic systems. So graphite's a good example of this. Graphite is a sheet of fused aromatic rings, right? You just have just this whole network of these benzene rings kind of fused together, right? Now that being said, instead of having it as a sheet, you could make a three-dimensional shape with that, and that's where Buckminster fullerene, named after the famous architect who came up with geodesic domes, basically architectural structures that kind of look like this. They're made of interlocking, hexagons and pentagons. They basically, once you start making this 3D structure, now you have either, you basically have fullerenes. You have buckyballs, that's a colloquial term for those, where you have about 60 carbon spheres. If you have larger ones, they're known as fullerenes, in the 70 carbon range. Basically, you have these large spheres of graphite, effectively. Okay. Now, good question is, how are these systems aromatic if they're not flat? It's You could consider this as sort of localized aromaticity. So if you consider each of these like flat parts with a benzene ring, they have their own aromaticity, their own sharing of electrons there, that delocalization of electrons. But it's not spread throughout the whole network the way graphite is. Which, by the way, this is why graphite's such a good conductor of heat and electricity, right? You've got this huge delocalized system of electrons, and that's why electrons can move in one direction. You've got an electrical current there. All right. Now, with buckyballs, or Buckminster fullerenes that are spherical, uh, you can also kind of extend them into tubes. So these are called nanotubes due to their size, right? They're really small tubes. And between Buckminster fullerenes and nanotubes, there are a lot of interesting applications you can apply here, just from the fact that they are able to store things or transport things, and they have interesting physical properties, like they're just like in terms of their tensile strength, their thermal strength, and so on. Okay, there's a lot of interesting cutting edge technology that's centered on this stuff. Again, due to the fact that you have aromatic systems creating this material. And that's it for this chapter. So let's go through the practice problems together. Let's go ahead and practice our nomenclature here. Let's name these compounds. Okay. If you're having trouble naming these, basically it might help to point out that this methyl group here turns this into a toluene. Okay. Likewise, you may want to look at this amino group here as your primary group and determine the name of this. Okay, so that's an aniline. Hopefully you remember that, or if you didn't, you can look that up. But go ahead and name these accordingly. Okay, so here are the names for these. So here we have 2,4,6-trinitrotoluene, more commonly known as TNT. That's where we get that name from, TNT. This is highly explosive, as you've probably guessed. Typically, anything that has a lot of nitrogens and oxygen, any organic molecule that has lots of nitrogens and oxygens on it, will typically be explosive. So here we have aniline here as our root word. And so that's the number 1 position. Oh, sorry, I forgot to mention that here. Here the methyl groups are the number 1 position, and that's why the nitro groups are the 2, 4, and 6 positions respectively. Okay. By the way, don't use ortho, meta, or para here when you've got more than 2 substituents, just because then it gets kind of confusing. So there you want to stick with the IUPAC numbering system. If you had only one nitro group sticking out here, then you could say, oh, it's ortho or it's para or whatever. But once you start getting more than one nitro group, that's where it gets complicated. Okay, over here, of course, we have our aniline, our amino group, at the number 1 position. So our 2 ethyl groups are at the 3 and 5 positions, respectively, and the nitro groups at the number 4 position. Please note from an alphabetical order standpoint, E comes before N, and that's why it's 3,5-diethyl 4-nitroaniline. Okay, it's not the numbers that cause that ordering; it's the it's the alphabetization of the E for ethyl and the N for nitro. Same like any other organic compound we've seen before. Okay, okay, this is more of a definition question. Explain how we know that aromaticity is stabilized experimentally. So basically, explain heats of hydration and how molecular orbital theory rationalizes that stabilization. Again, we show the pairing of electrons in our MO diagrams using frost circles and so on. So again, I've got the answer here, but typically remember on a quiz or exam, you're going to see more application-based questions than this stuff. This is more to see if you remember the concept behind the stuff we've seen. Okay, so I'm just going to gloss over that. Gloss over that. All right, there we go. Here's a more practical question. So go ahead and look at each of these and label them as aromatic, anti-aromatic, or non-aromatic. Okay, so let's go over the answers. So for this first one, over here, you basically have two ring systems, right? And now you've got to be careful here, because on one hand, if it's possible to have both rings be aromatic together, then sure, they will be. But look at the system you have set up here, right? So if this oxygen is involved here, right, which it would have to be to complete this aromatic system, you would wind up having an even number of electron pairs. So you've got 3 electron pairs here, right? And that this bottom ring is going to be aromatic. But when it comes to this here, you would have 3 more. That's 6 electron pairs in total. So this whole system would be anti-aromatic if this p, the p orbital on this oxygen with this lone pair was involved in this system. So to avoid that happening, this oxygen stays sp3 hybridized. This top ring does not get involved in aromaticity, and instead it's just this bottom ring that's aromatic. For these other 2 molecules, these are both going to be aromatic, right? So here we've got 5 electron pairs, so this whole fused ring system. This is basically like naphthalene with a nitrogen instead of a carbon, right? And of course this lone pair is not going to be involved. It doesn't have to be. We've already got our 5 electron pairs. Likewise here, this molecule is kind of like benzene, but with an oxygen instead of a carbon. Again, these 3 electron pairs are all you need for aromaticity. The lone pair on this oxygen does not need to get involved. Okay, let's try a synthesis problem. So go ahead and predict the major product for the reaction listed over here. Okay, so you've probably figured out we've got HBr, okay, and so it's probably going to do a hydrohalogenation, right? We're going to add HBr across the double bond. Probably not going to add across this this benzene over here, right? So it's probably this isolated alkene that we're going to add it across. Now that being said, which atom gets the hydrogen? Which one gets the bromine? So now you may have to think back, go back to your chapter on addition reactions and look up Markovnikov's rule. Okay, so the bromine adds to the less substituted carbon, right? Okay, and you're probably saying to yourself, wait a minute, I thought Markovnikov's rule says it should be add to the more substituted carbon. And that was the trick for this problem, right? So if you just memorize that rule with Markovnikov's rule, you probably would have gotten this answer wrong. You would have put the bromine on that tertiary carbon, thinking like, oh yeah, that's the more stable one. But remember, what's more stable than a tertiary carbocation? An allylic carbocation, or in this case, a benzylic one. So it's that benzylic site that is more stable as a carbocation, and that's why that was the one that gets the bromine. Okay, so watch out for that one. This was a pretty tricky question. Okay. Also, please note that because your carbocation is flat, that bromine can add to either side. So from a stereochemistry standpoint, note that you get both enantiomers. Okay, so here's an NMR problem. So basically, we've got an NMR spectrum, or for a molecule that has an NMR spectrum with these peaks, with these signals, and its carbon-13 spectrum has these signals. Okay, so go ahead and see if you can kind of predict the structure of this compound. Now, again, when you're going from data to a molecule, this involves kind of getting jigsaw puzzle pieces and trying to connect them together, right? So try and figure out, based on what's in what range, what types of signals you're dealing with. Also keep in mind that symmetry can kind of help account for any signals you have missing. Okay, so take a second and try this out, and then we'll go through the answer. Okay, so if you're back, you've noticed that we have 8. We have 8 aromatic signals here. We also have 8 aromatic signals here in that 100 to 150 range. Okay, so that's something to keep in mind. That's kind of interesting. Over here we have a triplet that integrates to 3 protons, okay, which is kind of interesting because normally for like a methyl group you'd have like a singlet if it's an isolated methyl group. So it'll be interesting to see what this is. We have a singlet over here that integrates to 3. That's more indicative of your isolated methyl group. Okay, and here we have a quartet, and that has 2 hydrogens. So we probably have it's probably a methylene group of some sort that's being split by that triplet. Okay, so that kind of is usually indicative of a so if you see this quartet and this triplet here with 3 and 2 respectively, that probably indicates they're linked, right? So this is not an isolated methyl group. This is probably part of an ethyl group. So we probably have an ethyl group over here, okay? And then we have another methyl group that seems to be isolated, okay? Now, this methyl group is over at 2 ppm, so I wonder if that means that it's attached to the benzene ring, and we've probably got a toluene, and that's what's shifting it downfield, okay? So if we look at our molecule here, we see that's the case. Our benzene ring over here has a methyl group attached to it, and here we have an ethyl group. So those were kind of straightforward. Okay, the fact that we had 8 aromatic signals told you that you're dealing with more than one benzene ring. Okay, because as soon as you saw that there's an ethyl group attached to, or a methyl group attached to the benzene ring, and the fact that you have an ethyl group, and that ethyl group probably was also attached to, to a benzene ring, because this CH2 group is shifted downfield. That tells you that you would have only 4 aromatic protons, right? Because 2 of those other positions are taken up with a methyl and an ethyl group. So the fact that you had 8 tells you that you've got more than one benzene ring. Okay, so here's kind of how that can work together. We've got 2 benzene rings that are linked to each other, and those, and then there's a methyl group and an ethyl group on those respectively. Okay, for the carbon-13 spectrum, we've got 8 different aromatic signals. Okay, so we've got 1 over here. These 2 are equivalent. These 2 are equivalent. So that's 3 signals, and there's a 4th one here. Here's a 5th one. These 2 are equivalent, so that's the 6th one. These 2 are equivalent, so that's the 7th one. And there's the 8th signal over there. Okay, so again, that kind of tells us that we can't be dealing with one benzene with 2 groups, because the symmetry alone would have cut down the number of signals, right? So the fact that we've got 8 different signals tells us that we have 2 benzenes, and that's how, that they must be connected in such a way that allows some of those signals to get cut out, to be equivalent, and therefore we see fewer signals, right? So out of our 12 aromatic carbons here, we only see 8 signals. Okay, so that tells you a little bit of how these two, symmetry of this molecule. Okay, and of course there's 3 non-aromatic signals. Those are the 3 alkyl carbons that we have over here. So that makes sense. Now, if you struggled with that problem, and these aren't these types of problems aren't easy, keep in mind that you can work through these problems backwards. Your quizzes and exams and so on are all multiple choice. One of those answers has to match up with a question. So if it's easier, look at your answer choices and ask yourself, okay, I've got this answer choice here. What signals would I expect to see for this? And then see if that matches up to the question. That might be a little bit easier when it comes to solving some of these problems. Okay, but like I said, it's if you were trying to do this in research or something, basically it's kind of putting together a jigsaw puzzle piece. Putting pieces together. So you can kind of see how I approached the clues from the integrations and the splitting to figure out what kind of pieces these were and see how they were linked. Okay, so for example, quartet let you know again that it was close to probably something that had 3 hydrogens, and this triplet, of course, was being split by something that had 2 hydrogens. So, that's indicative of an ethyl group. So that's kind of the approach you kind of take to some of this stuff. Okay, but again, don't panic if if the problem seems kind of a little bit difficult when you approach it from one angle like that. You could try going backwards. That's it for this chapter. Now, this is a chapter, this is the fourth chapter we've covered this semester, which means we have an exam coming up on chapters 15, 16, 17, and 18. So there is no quiz on this chapter, so please try the practice quiz that I've posted on Blackboard. It's in the content section. It's a PDF file. The answers are on there, so you can use that to help, to grade your work, as well as go through your old quizzes for chapters 15, 16, and 17 to prepare for the quiz. And of course, for this chapter, don't forget to try the homework out for some of the more procedural stuff we've learned. And as always, let me know if you have any questions. All right, so good luck on your exam, and I'll catch you in the next chapter.